Welcome to Caver Course. I am Erin Caver. I'm a junior animal science major at Tuskegee University, and today I'm going to talk to you about how we hear the things that we love to listen to, such as music or a person singing, things like that. So we're going to go on the physiology of how sound is conducted or perceived in your ear. So we are first going to talk about the structures within the ear. The ear is divided into three sections. Those three sections include the external, the middle, and the inner ear. So to start at the external ear includes your pinna all the way to your ear canal to your tympanic membrane. So the pinna is like the outer portion of your ear that we pierce. Also, it can vary in shape and location depending on the species you look at. So a dog's ear or pinna will look different from my ear or pinna. And then the eardrum or tympanic membrane is a membrane that divides the middle ear from the external ear. The middle ear is composed of three bones. Those three bones include the hammer or malleolus, the ambus or incus, and the stirrup or the staples. The malleolus is connected to the tympanic membrane, and then it is connected to the incus. The incus is then connected to the staples, and the staples is connected to a membrane called the oval window, which leads into the inner ear. The inner ear is composed of a structure called a cochlea. The cochlea is a fluid-filled structure that kind of resembles a cinnamon roll. When you stretch it out, there are three different layers. You have your vestibular duct, or your scala vestibuli, your central cochlear duct, or scala media, and your tympanic duct, or scala tympani. The vestibular duct and the tympanic duct are similar because they are both on the outer layers, and they come to join at a point called the heliocotrema. Now, they are also both filled with fluid similar to the plasma in your blood. The central cochlear duct, however, is a dead-end tube that is in between the vestibular duct and the tympanic duct. The central cochlear duct is usually where most of the sound perception is going to occur. It also has a structure in it called the organ of Corti, which has hair-like cells or hair cells that are going to be prominent in sound perception. Get to the interesting part, the actual physiology of hearing. So when a sound vibrates through the air and hits your pinna, it then travels down into your ear canal and hits your tympanic membrane. This causes the tympanic membrane to cause a vibration that goes through your malleolus all the way to your staples. Now, the thing about the middle ear is that there is a muscle there that prevents loss of sound due to friction. So it basically amplifies the sound so you can hear it as it was and it won't dampen. Now, once the staple vibrates, the staple causes the oval window to vibrate. Now, this causes a fluid wave to go into the cochlear duct, and in the cochlear duct, as we mentioned earlier, is the organ or structure called the organ of Corti. Now, the organ of Corti is a structure kind of similar to a mat where it has different hair cells on it, and then it is also composed of a tectonic membrane. So when the fluid wave comes rushing across the tectonic membranes, it causes up and down propagations, which cause the hair cells to bend. So the hair cell is now bending like to this or to the left or to the right, either way. And the hair cells have stereocilia on them, which are little hair-like projections that are arranged from shortest to tallest member. So when the stereocilia are leaning towards the tallest member, that is allowing tip links, which are proteins on the stereocilia, to open ion channels and allow neurotransmitters to be released. So this opening of ion channels allows cations to rush in and cause a depolarization, and the depolarization is moved along as an action potential along the brain nerve 8, which is the vestibulocochlear nerve. Now, all the stereocilia are leaning towards the shortest member. This causes the tip links to close all ion channel gates and stop neurotransmitter release. This stops all depolarization and stops the action potentials. Now, when the stereocilia are not moving towards either way, the ion channels are about, 10% of the ion channels are approximately open. Which means that at rest there's even a depolarization and an action potential. Now, this change in action potential intensity and no action potential shown here causes a sort of a pattern to be sent into the cranial nerve 8 to be processed into different sounds of different intensities, loudness, pitches, and frequencies. An action potential is when a cell becomes depolarizing, causing the membrane potential of the cell to become more positive than what it was before or at resting. So when the tip links on the stereocilia open the ion channels, cations such as potassium and calcium were able to go into the cell, causing it to be more positive than what it was, causing a depolarization. This depolarization is then put into an action potential. And if you remember the patterns that I showed you earlier, that signal is sent to the oblongata from nerve cells and then to the cerebellum. This is where it is going to be processed into different frequencies and pitches and loudnesses and intensities. So overall, the vibrations from sound waves go from your pinna to your eardrum, through your bones in your middle ear to your inner ear where your cochlea is, to the organ of corti, and causes the stereocilia to bend in different directions, causing action potentials to be sent through your cranial nerves in different patterns to your brain where it can be processed, and to certain sounds based on the locations of where the sound came from in the hairs or the stereocilia. So, thank you for listening to my video of how hearing works, and I appreciate you for staying this long, and I hope you enjoyed. Thank you very much.